out into the, okay, no, that's good. And I'll look out into the future a little bit. Um, so to begin, I'm sure you've seen, maybe they're like cliche at this point, right? And we were thinking about weather and climate quotes like this, sometimes attributed to Mark Twain, but I don't think it was actually him. It seems to be not actually his quote, but right, that climate's what we expect and weather is what we get. Or this is a more modern one from a colleague, Marshall Shepard, that weather's like your mood and climate is like your personality, right? So there is uh, it's a fuzzy line in between, right, between weather and climate, and they intersect with each other. And that sort of, my career very much started in weather, as I'll talk about, and then but it kind of included aspects of climate, and now my job is in sort of both spaces. But I think there's actually a lot of good opportunity to overlap them and integrate them, and that's a bit of what I try to do. So a little bit about me and kind of how I got interested in this. Actually, this is usually what I use as my origin story of getting interested in meteorology. I grew up in Minnesota. This was when I was a kid. This tornado was live on it says Channel 11 live. This was live on the evening news. It was a news helicopter up to like look at the traffic or whatever, and then this tornado develops, and this is still one of the very best tornado videos I think that's ever been taken, in terms of seeing the dynamics of how the tornado is behaving, and it's dissipates and it forms again, and you see trees getting tossed around. Now people get videos like this with drones for somewhat regularly, but this was just, imagine you're a young elementary school kid, kind of, and there were only 3 channels on TV, so that you didn't have a lot of choice. But this was something that got me very fascinated, and interested in weather. And then the Weather Channel was also kind of new at this time, and I watched a lot of that. So I was interested in kind of interesting extreme weather. So when I went to college, I got my undergraduate degree in meteorology at Valparaiso University in Indiana. And did a summer internship at the National Severe Storms Lab in Oklahoma. Ended up getting to go out and drive those cool instrumented vehicles around near storms. So that was sort of exciting. And then I came here to CSU for graduate school. So came to the atmospheric science department. Probably, I don't know, have any of you even been out to atmospheric science before? So we're out at Foothills campus. If you go take LaPorte out to the west, you'll see our buildings up on the hill there. Kind of can't miss it. And then that's me at graduation with my PhD advisor. And a couple of sort of formative things while I was in graduate school. Obviously, you're in graduate school, you're doing research and taking classes and learning and all of that. But 2 very formative experiences for me were attending these workshops on relevant topics. So on the left was a workshop that they did at the National Center for Atmospheric Research in Boulder, on convective forecasting. So forecasting thunderstorms, which was a really new and emerging thing at the time. I mean, it still is. Still, we don't have that problem solved by any means. But in any case, a lot of the people pictured here are now colleagues, or they were the folks giving the lectures at the time that I collaborate with. And on the right was a workshop it was also based in Boulder, called Weather and Society Integrated Studies, or is. And this was a very interdisciplinary group of people studying, weather forecasting, social science, communication, all kinds of different fields. And it was really eye-opening in terms of, oh yeah, like, we're studying how to forecast the weather better or the climate better or whatever, but like, how do people actually use that information? How do you study that? So it was a really cool experience. And so the main reason for showing this is that if, you know, in your graduate school career, these kinds of things, you know, these may not be the specific kinds of things that you're interested in, but if these kinds of things develop where you can go and like hang out with a cohort of your peers for a week and just kind of get really immersed in a topic, you know, it's great. And then you might end up collaborating with these people for, you know, for in the future, or continuing to run into them at conferences or whatever it might be. This is a picture of my, well, now a couple of years old picture of my research group. A couple of these folks have graduated and moved on since then. But in any case, how I tend to describe my academic research, so I still have these kind of two hats of the academic research group and then the climate center, and sometimes they intersect, which I'll talk about a little bit later. But most of my research over my career has been aimed at advancing understanding and prediction of high impact weather, and a particular focus on extreme precipitation. And so this was my first paper. This was my master's thesis research. And basically trying to figure out what kinds of storms. So at this time, having enough radar data to do like real analysis from like the National Weather Service radar network, like that, there was finally, you know, 5-7 years of radar data, so we could do this sort of study and basically just look at what are the characteristics of storms that produce a lot of rain. This is the only equation I'll show you today. It's a very simple equation, P equals R bar times D. So the precipitation at a location, right, that's going to fall in that gauge, equals the average rainfall rate times the duration. So this is sometimes called the first law of precipitation forecasting. The most rain falls where it rains the hardest for the longest. So it's like super simple, it sounds like, but then, you know, you try and actually make predictions of this and it's quite difficult. So what kinds of storms maximize R and or D, right? Have high rain rates that last a long time. These are like schematic diagrams of the types of storms that produce, based on what they would look like on radar, of the types of storms that often produce very heavy rainfall. You think of other, so you might first think of like hurricanes, like that's pretty straightforward how a hurricane makes a lot of rain. But we were looking at these convective systems, thunderstorm complexes more in the central part of the country that had not been studied quite as much. So in any case, in the one on the left here, imagine you have a line of storm cells here, and you're located at some location under one of these. Everything here is moving from left to right. So basically these cells are lined up like a train on train tracks. And so if your location is under here, you're going to be repeatedly getting the heavily raining cells and accumulate a lot of rain. Or on the right, same sort of idea. These tend to be a little bit smaller, but what happens is you get the individual cells are moving from left to right, or usually west to east. But then new ones keep forming behind, right? And same idea that if you're located around here, you can add up a lot of rain in a short amount of time. And here's an example actually this is from Eastern Colorado, just a couple of summers ago, August 2021. The little blue dot, if you can see that there, is our coagulate station at Holyoke, or just like southeast of Holyoke. And so there's the radar animation there, and then you can also see the rainfall accumulation time series on the graph in the upper left. So there, it just started over again, and you can see some of these processes at work when the really heavy the deep reds, the really heavily raining cells move over. You see the rain accumulation jump way up. Looks like the storms are gone. Oh no, here's some more cells that are moving through. We'll add another couple of inches of rain on top of that. So this was a huge, very localized, but really high impact event out in Phillips County back in 2021. In that area. And so this is, this is an example of some of the things that we look at. But, I think it helps to take a broader perspective. It's some of what you're all here for in a interdisciplinary kind of class, right? And we think about floods, and they're really by nature interdisciplinary. So if you think about getting a flash flood or a river flood, different time scales, but either way, it starts from having a lot of rain, right, or snow, but you think about it, rain. So what's going on in the atmosphere to get all that rain to the ground? That's kind of my background and expertise in the meteorology and atmospheric science. But sort of meteorology ends when the water hits the ground, right? But if you're thinking about flooding, then what happens after that? Now you're in the realm of hydrology. You might want to know, how does flooding impact people? So now we're into maybe in the social sciences, looking at sociology or economics. This might also be emergency management. You can think of all sorts of other fields that would be relevant here. Maybe you're interested in what happens to the ecosystem after you have a big flood. So that might be ecology or other fields. We might want to know how floods are going to change in the future. So now we're looking at climate change, but also floodplain management, city planning, where do we build our buildings, policy, all these kinds of things, right? So if you want to understand floods, it helps to, in your, if you're doing PhD research, right, you're going to be focused on some particular area, some very specific topic. But I don't really like to over specialize myself, and it's good to kind of take the step back and see where we're at. So after I started here at CSU, I was fortunate to get a career award from the National Science Foundation. And one of the things that I did as part of that project is hosted this workshop. Well, it was a kind of a recurring workshop that we did it twice with the same group of people. So this was for graduate students studying it's kind of a little bit like this class, I suspect. So it was graduate students studying extremes or rain or flooding or things along those lines. And it was a really, really cool group. We had statisticians, we had a historian, we had meteorologists, hydrologists, of course, economists. So just a social scientist, people studying emergency management. So it was a really cool group. And what ended up happening was we had the first workshop here in Fort Collins in June of 2013. And some of you might know what happened not too long after that, a really big flood here on the Front Range. And the plan was to bring the group back together in the second year in a place that had a flood, and we were going to go kind of do that. So we did a tour of places around the Front Range that had flooded before, like Big Thompson Canyon when we were here in 2013. And then the next year when we came back, then we got to go see some of those same places and then other places around like Lyons that flooded. So it was kind of a particularly meaningful experience in that way. What my research group is working on now, one of the big topics that we focus on is applying machine learning to high impact weather prediction. So we've like some of my graduate students, and this is Aaron Hill up here, who was a postdoc in my group, but now is a faculty member at Oklahoma. But developed this forecasting system for heavy rain and then for other hazards like tornado, hail, wind, and tried to get it into operations in the National Weather Service. And it took a long time, but that succeeded. This is my student, Allie, here, talking with the forecaster at the Storm Prediction Center in Oklahoma. And so the forecasters are using our tool every day now. It's not the only tool in their toolbox, but it's another tool that they have to give. And especially this is what we've learned from them, is it helps improve their confidence. It doesn't always tell them something they didn't already know or they weren't already anticipating. But when our system has a high probability in a certain area, like they pay attention to that, and it can help give them more confidence in their forecasts. And then kind of related to this, we may do this class again in 2 years, in 26, but Libby Barnes in our department, who's an expert also on machine learning, but more for climate, and then I do machine learning for weather. We've done this class this fall, which we just totally are kind of making up as we go, but for weather to climate data-driven forecasting, it's been really interesting and fun. machine learning, AI systems are in some ways already revolutionizing the way we do predictions in this field. And so we've kind of been exploring what's good, what's bad about these systems, and getting students running these systems and kind of seeing how they do. So that's been sort of fun. So I'll show you here just a quick example of what our machine learning forecasts look like. So this was from Helene just a few weeks ago, a month ago, that led to the devastating flooding in Western North Carolina, Tennessee, Georgia. These were the forecasts from our excessive rainfall model going back. So these are all valid on the day of the heaviest rain. So this goes back to 8 days on the lower right, 8 days ahead of time through 6. So the lower row here, our model and really no forecast models had much of any indication that there was going to be this heavy rain, let alone even much idea of a hurricane in that area. So not very good at that lead time. And even at like day 5, not very good in the area where the heavy rain would occur. But then once we got in a little bit closer, like day 3, now we're getting some very high probabilities in that Georgia, North Carolina, Tennessee area. Those go up on day 2 and day 1. And then this is where, like everywhere shaded in blue here, is where excessive rain occurred or flash flooding occurred on that day. So it captured it pretty well at these short, really highlighted the high risk on the day 1 and 2, but not much signal, so depending on your decision-making timeline, these may or may not have been helpful, but this is the kind of stuff that the system, so it's fairly broad brush. It's not like trying to predict, floods in specific watersheds or anything like that, but it's especially to inform the forecasters that are doing national scale forecasts of these different hazards. Okay, and so kind of this starts to lead then into, as I was started as a postdoc, as a early career faculty member, in addition to the stuff I was doing sort of for my real research for funded projects and that sort of thing, we have fascinating weather here in Colorado, right? Like that, you all are familiar with that. So as sort of side projects and just as interesting things happened, my advisor that was always something he was interested in, was trying to figure out how these weather systems work in our complex terrain here in Colorado. So studied this kind of interesting case of banded snowfall in 2007, the kind of weather associated with the blow up of the Waldo Canyon fire in 2012, which was interesting. And then of course the flood in 2013. So these were all high impact events that in some way started looking at, and this starts to lead towards me becoming the state climatologist later. One particularly interesting one that I want to highlight was the Windsor tornado. I don't know, anybody go through anybody from the local went? No, okay. I have actually have a graduate student that just started this year who was a kid, in Windsor that their house got damaged, and now he that was his origin story, and he's now a graduate student studying atmospheric science. So anyway, this was May of 2008. I guess loop it again. This was unusual for a lot of reasons, so that you can see the storm in the radar imagery in the top right there. So the storm was an EF3 tornado that went through Windsor, did a lot of damage in Windsor. So that's unusual kind of on its own. But what you see is the storm is moving towards the northwest or northwest. That's pretty unusual. So this was quite an interesting case. And so with colleagues here at CSU and NCAR, my wife was listed on there as a co-author. We took a look at this case from a few different perspectives. And so one was just like, okay, what's the history of tornadoes around here, and have any of them gone to the northwest? And it turns out, if you look back far enough in the records, there are some that are kind of like that. focus here just on the maps on the left are going to be hard to see. Just focus on the one on the right. So these are all the EF2 or greater, stronger tornadoes along the Front Range up until kind of through that tornado in 2008. And then the ones that had a component toward the west are in green. So the Windsor one is here, the long green track. But there's a few other ones in there, right? Like from the past. So it's not totally unprecedented, but this one was especially strong. But most of them are, even the long track ones, are moving toward the east. And so we incorporated some social science methods into this work and interviewed a bunch of different decision makers here along the Front Range. And I'll just kind of highlight this quote from one on the bottom here, that essentially the person knew the climatology in some way of tornadoes here on the Front Range. Tornadoes usually go to the east, right? So if you're in a location and there's a tornado to the east of you, you probably are not going to be worried about it. And 90% of the time, that's going to be right, because tornadoes don't go towards the west, except when they do. And they did in this case. And so that official actually sort of disregarded the threat because that tornado was going the other way. But in fact, it was coming towards them. And so you can kind of see, the reason I bring this up is just to see how the intersection of the weather event that happened on this day, but then the broader climatology and our human perceptions affect all of this. And it's not just like, did you make a good forecast of the tornado? There's a lot of other things at work here. Okay, so that then brings me to Nolan here. So that's Nolan Duskin with the rain gauge at the White House. And so Nolan is a legend in Colorado and in this field of climate services more generally. So Nolan was in this role for about 40 years. He was the assistant state climatologist for 30 years, and then the state climatologist for 10 years. He's still around. He's still, active. I got an email from him this morning. But he really kind of was a great, a person who made being a state climatologist all that it can be. But so Nolan retired in 2017, and when he was retiring, then the university was trying to figure out what to do with the state climatologist position. Anyway, then I applied. People approached me about, hey, are you you do some work kind of in this area, you might be good at it, or are you interested in this? And I applied for the position and got it. So I became the state climatologist in October of 2017. So it's 7 years now. And so a little bit about the Colorado Climate Center and state climate offices in general. So this was actually a federal program up until 1973. So it was a program of NOAA to have a state climatologist in each state, mainly for serving the agriculture sector, but for other reasons as well. But in 1973, that was done away with at the federal level, and all the states kind of got to decide what to do at that point. What a lot of states did is went to the land-grant university and set up a state climate office there. And that's what happened here in Colorado. So we don't know the exact date. Sometime in 1973 or 74, the Colorado Climate Center was established with initial support through the Ag Experiment Station in the Department of Atmospheric Science. So if you look around at state climate offices now, there's quite a few that have a model like ours, where it's at the land grant or the ag school. But some states where it's in state government, like in the water resources or the agriculture department. I think Arkansas is currently the only state without an official state climatologist. So it's kind of a hodgepodge. There's no, like, in some states it's defined in state statute. That's not true in Colorado. It's always just been a thing that happens at CSU. So it's kind of a lot of different models out there. But there's I guess now also a little bit outdated photo of our team that was out on the football field just this past summer. But Becky Bollinger, who's in the front middle there, was the assistant state climatologist. She recently took another position. So we're going to be hiring and then Peter Goebel, who's in the back, second from the left, is now the assistant state climatologist, and we're narrowing down for the person to kind of step in sort of to his role. But the way we talk about our mission is threefold. So we do climate monitoring. I was talking with Karen about this a little bit at the beginning. If you went back 30 years, like archiving the paper records of the weather data would be a very core role of a state climate office. That's not as important now because all the data is digitized and you can get it pretty easily on the web. But we run two observing networks that I'll talk about in a second to collect data in addition to trying to keep track of all the other data sources that are out there. Some applied climate research that I'll touch on briefly, and then climate services, which I'll also come back to in more detail in a little bit. So a couple of unique things that run out of our office. One is COCORAS, the Community Collaborative Rain, Hail, and Snow Network. So this was founded by Nolan Duskin after the 1997 flood here in Fort Collins. So I hope you've all heard about the 97 flood by this point, right? Or you've seen a high water marker in the engineering building or by the Dairy Queen or elsewhere around town. So this was a huge disaster for Fort Collins. Very, very localized storm over the west, like near the old football stadium, west side of town. Huge damage to campus. Morgan Library, flooded. 5 people were killed in what used to be a mobile home park that kind of near where the Dairy Queen is in that area now. So huge disaster. And one of the scientific challenges with this was that it was so localized that there was really no data. The radar estimates were not very good. So there was very little data to say how much rain actually fell. Because here on campus, I think it was 4.63 inches from that storm, which is a lot of rain that's the wettest day on record for campus, but it was more than double that on the west side of town, which they only found by going around and doing what's called a bucket survey, basically like looking for buckets or other things that collected water. And so Nolan realized that if you could get people to get this plastic rain gauge in their backyard or their school or their farm field or wherever, you could get a much more detailed picture of how much rain fell, right? So that was the idea. It started in Fort Collins. So if you look in the upper right map here, this was 5 years in 2003. It was still just Colorado, but it was starting to build up quite a few observers in Colorado. This is 2008, year 10, and then year 25 last year. So this is our 26th year of this thing that started as a little community thing in Fort Collins and is now nationwide, international. 2/3 of the daily precipitation observations in NOAA's data set come from volunteers with these rain gauges in their backyard. And this is like the number of reports each year. So just kind of a remarkable participatory science success story, and just continues to grow. And so if you have, I know as college students, it's grad students, it's often, may not have a place with a yard that you can put a rain gauge, but in the future, think about it. Or if you have family, friends who would like to collect rainfall, it's very easy. You get this gauge and you put it in your yard, and then for the last 45 days here in Fort Collins, you go and enter 0 in your in the app. But yeah, so that's kind of all there is to it. And then the other thing that we operate, and a lot of state climate offices operate, is what's called a mesonet, basically a high density network of weather stations. These are automated weather stations. And so there's a map around Colorado of where the COAGMET stations are. Actually, we've added a couple since I've got to get the updated version of this map in here. There's a couple more that aren't shown here. So this has a history at CSU going back to the early 90s. The Colorado Agricultural Meteorological Network, or COAGMET, kind of started as CSU ag researchers needed weather data to do their research, and now has grown to over 90, I think 95 stations around the state. And so these are high quality automated weather stations. We collect, temperature, humidity, solar radiation, wind, increasingly, well, soil temperature and increasingly soil moisture, rainfall. And so it's measuring all the things that you need to estimate reference evapotranspiration. That was the original key use of it, was evaporative measuring or estimating evaporative demand. But now it's used by, with the data goes in real time to the National Weather Service, used by meteorologists and of course, and ag producers and researchers and et cetera. And so all the data is freely available. And we just rolled out a new website. So in the past, the website was like a bunch of text and links. Now it's a cool interactive map. That's not a map from today, although it's actually, the temperatures today are pretty similar to that. But coagmet.colostate.edu, you get the interactive map, but there's an API if you want the data, you can get graphs, you can get other types of maps. So this is kind of a big part of what we do as well. And then we also, as part of this, operate the campus weather station. Hopefully you've either noticed it or maybe you've been over there on a tour or something over near the bus station. So this has been on campus since 1879, at that exact spot since 1961. So we have long records here for Fort Collins and for CSU. You can listen to Nolan talk for like an hour about this one weather station on this video if you're into that sort of thing. Okay, so what else do we do as the state climate office? So drought monitoring and analysis. So this is kind of my journey, right? Is like I started, and my main like research expertise is on the other end of the extremes, right? Heavy rain and flooding. But drought clearly is a huge issue in Colorado, and state climate offices play an important role in drought monitoring. So our office makes the recommendations for Colorado for the U.S. Drought Monitor, and then passes them on to the author, the national author that week. And we look at all kinds of different indicators. In the winter, it's snowpack in the mountains. In the summer, it's evaporative demand, temperature, rainfall, of course. Stream flow, reservoirs, you name it. These are all parts of drought and drought impacts. So this was a big learning experience for me to start thinking about things on the dry side of the extremes. But now we've got good experts in the office on this as well. So that's a part of what we do. So just to kind of highlight how challenging this can be. This is a paleo reconstruction of drought in Colorado, going back to the year 100 or so, somewhere in there, reconstructed from tree rings and things like that. So this is the percent of Colorado in drought from this reconstruction, going back, a couple thousand years. And so drought has always been an issue in the West, right? Like you study water, right? That. And then this is more recent, a somewhat more recent period. This goes back to the late 1800s. This is short-term drought. So this is like 3-month time periods, the percent of the state that's in what you consider drought conditions based just on precipitation. And at this time scale, it's essentially always there's somewhere it's very, very rare that there's no drought anywhere in Colorado on short time scales. But here's longer time scales. This is 2 year accumulated periods. And now you see the droughts that, you've probably heard of or that people talk about, right? Like the turn of the 20th century drought in Southwest Colorado was devastating. The Dust Bowl, of course, in the 30s and the 1950s, and then the more recent drought periods of around 2002 and 2012 and 2018 through 20. And again, this is precipitation only. So when you start factoring in the effects of warming, rising temperatures, then this picture tilts a little bit, which I won't get into here today. But this is the kind of stuff that's in our Climate Change in Colorado report. So this is an updated edition that had the previous version was last updated in 2014. And this with the updated version just came out in January of this year. So climatechange.colostate.edu. Becky Bollinger was the lead author on this, and it was led by our office. So lots of information there to check out if you're interested. I'll highlight just a couple of things here. So we started looking at the key climate variables, temperature and precipitation. It's been warming. It's expected to continue warming with very high confidence. But precipitation is a different story. Recent trend has been downward, but we don't know whether that's going to continue. And so there's sort of low confidence in what's going to happen with precipitation out in the future. But here's observed temperature going back to the late 1800s for Colorado with respect to the late 20th century average. So blue bars are years that were cooler than the late 20th century average. Red bars are warmer. A lot more red bars than blue bars in the last 30 years or so. So statewide, 7 of the 9 warmest years on record have been since 2012. This year will most likely end up in somewhere in the top 10 or probably in the top 9. So that will have to, change that stat again after the end of this year. But then here's precipitation. And there's no long-term trend in precipitation in Colorado, at least not in the statewide average. So instead, what you see is this variability, right? You get years and decades that are wet and dry and wet and dry. And you can see like we've got 4 of the very driest years that we've ever had within the last 20s. 2002 is the driest water year on record for Colorado statewide. And this is 2012 and 2018, 2020, but with some wet years mixed in there as well. So it's always more complicated with precipitation. And this is kind of the same story looking out into the future. So this is future projections of temperature. The black line is observed up to this point. These are 2 different sets of climate models out into the future under a moderate future emissions scenario. So this is not the like high end, worst case kind of scenario, but still more warming expected, of course, out into the future. And if we look at this in a bar graph, it's so where we've come to this point is in Fahrenheit about 1.5 degrees from the baseline used here. Another 2 to 4 degrees-ish expected in the projections by mid-century, which is not that far away. So continued warming expected, and that's with pretty high confidence. But if we look at precipitation, the models are sort of all over the place. So here, 0 would be no change. So yeah, there's some climate models show Colorado getting wetter, others show it getting drier. Others in between. They do mostly show even more variability. That is one kind of constant theme. But we really don't know what's going to happen to precipitation in the future. So this is kind of the uncertainty that we're dealing with in the water space, right? Is we know it's going to get warmer. We don't quite know what's going to happen with precipitation, and then got to figure out what's going on from there. So that leads, chapter 3 is all about water. This was funded by Colorado Water Conservation Board, so had to focus on that. And I think this is really the key issue of climate change in the West. Again, you've been hearing all about this semester, is climate change's impact on water. So things like, less confidence in what's going to happen with snowpack or like total stream flow, but timing of earlier runoff, high confidence, and especially high confidence in hotter summers, meaning more evaporative demand, lower soil moisture, more demand for water, especially. So I'm not going to go into, you can kind of get into the report, and then chapter 4 is about hazards and extremes. So, increases in heat waves, which makes droughts and wildfire threat worse. Probably more extreme precipitation, although we don't have a lot of signal of that here in Colorado, at least not yet. That's a pretty strong signal in places with more moisture closer to the coasts. And then other things like windstorms and hailstorms that we don't know as much about. So that's kind of the summary there. Okay, so another fun thing, that was just kind of a fun sidebar. A fun thing that we get to do as state climatologists is confirm or deny state records. So we've set the new state hailstone record twice in the last 5 years. The one on the left was from 2019, the 5 1/4 new record on the right from 2023. Here's the 3D print of the one on the left, so you can pass that around. It's a little too heavy. It wasn't actually quite that heavy, but in any case, but that's the shape and size there. So that's kind of a fun job as a state climatologist. But also connects to some research that one of my former students, Sam Childs, is doing, looking at future risk from hailstorms in Colorado. And it turns out so there's a climate change component to it, in that climate, generally as it gets warmer, there's will be more frequent favorable environments for severe hail in Colorado. But like the impacts of that are highly dependent on what happens with people and population growth. So if we continue on sort of a early 21st century population growth in Colorado, the hail risk just gets huge, right? And we've seen that to some extent already. But there's other scenarios where maybe the hail shifts out to the eastern plains more than it has been. And so that reduces human exposure, but increases agricultural exposure. So it's kind of intersecting uncertainties here that, make this an interesting and challenging problem as well. And so this is one kind of thing where actually my academic weather research overlaps well with looking out into future climate and so forth. Okay, so let's kind of get down to the final part here, which is what you've been hearing about in this class over the semester, and thinking about careers and future careers and so forth. So water in the West, right? This is what you're here studying. It's a huge issue. It's going to continue to be a huge issue. One of the reasons being that making decisions about water in the West is decision making under deep uncertainty. We know the climate's getting warmer, but we don't really know what's going to happen with rainfall or snowfall. We don't know what's going to happen with demand, all these things. So this is going to continue to be a huge issue that you're all going to be, hopefully making contributions to. And it's one that needs a big picture perspective, right? Like we can look at climate change projections, but that's only one little piece of this, right? It's engineering, it's natural resources, business, ag, ecology, humanities, policy. Like you can think of all the fields that this touches, right? So think broadly about it. That's hopefully the message you've been getting in this and other classes is that if we all work together, we can solve this. But if we all say, well, I'm going to run my climate model and then that's the end of it, like that is not going to be all that helpful, right? And I think actually in Colorado, people in the entities in Colorado are a great success story in this, where yeah, sometimes disagreements and politics gets in the way of it, but you've got a huge community here of people who want to, and I'm sure Karen can back this up, people who want to work together and figure out how to solve this. And that's kind of an exciting, so it will continue to be an exciting and challenging career field to be in. And then more specifically for climate services, this is kind of our core mission as one of our core missions as a state climate office. This is the sort of thing that gets attention all the way up to the White House. This is a report that was issued from the White House in 2021 on climate services and making this better and improving it. It might be hard to read the text there, but look at all these questions here on the left, and some of them relate directly to water, right? Is water for crops or livestock? How do we build infrastructure? Where can you have a house that's, without worrying about wildfire and storm surge, and on and on and on, right? And so, what we like the broader community need to do is, right? So we need actionable climate services that meet the needs of a diversity of users, working with the private sector to make this happen. So these are all big challenges that we can hopefully contribute to, and you can contribute to. And I'll end just with these are two actual messages from the last month that I've gotten that kind of relate to this and relate specifically to water. So this is from someone that we work with at a large water utility that you've probably heard of, asking about how do we incorporate climate change in our projection, in our own internal forecasting, right? We figured out that if we're using temperatures from 30 years ago, that's not going to be that's not going to give you good information out into the future. But you also know that rainfall is highly variable and anything can happen here in Colorado. So what do we do? How do you know, what kind of, how do we shrink the data set, whatever? So these are like real questions that people are that want to know the answers to. Or this is from someone on the Western Slope. Can you give us some recent drought information and what the drought impacts are on ecosystems, habitats, snowpack, monsoonal rains, wildfires, all these things, right? So these are the questions that decision makers are asking us all the time. And you can, there are so many different kinds of it's kind of core to what we do in a state climate office, but there's so many careers out there where these questions are only going to be more, in demand as climate changes and as we have more data to be able to actually answer these. So I think this is, it dovetails nicely with the question that Karen asked me at the beginning, right? Is like, we don't have to fax people weather data anymore or keep all these paper records. Everybody can get the data. That's easy. But what they really want is they want knowledge, they want insights, they want context. And that's hard for a spreadsheet to do or even for AI to do, right? So this is where your expertise can come in, whether it's in climate or it's in water or whatever. And this field is growing. It's, there's demand for it in the private sector because businesses have to care about climate change. And of course, research is a big area as well, and at the intersection of all of these. So I think it's an area that is going to continue to be in demand. So that is all I have. There is, well, it's covered up. It's climate.colostate.edu is our website, and my email if you want to get in touch. We do monthly state summaries, so you can subscribe to those if you want, or if you want to really dive into the data, we blog from time to time on that. So I will stop there and happy to take any questions. Hopefully I didn't go too long.
No, that's perfect. Yeah. Any questions from Right. What kind of data is using for soil prediction? Like, is it a simulation or something? Or is it also field as well?
Yeah, so yeah. So the question was about like this is like for the machine learning system, right? Yeah, for the machine learning forecast system, what input data are we using? So right now, the way the system is set up is that we actually use the output from the weather prediction model from the GEFS, the Global Ensemble Forecast System, if you're familiar with the different models. So we take the dynamical model output, but that's at pretty coarse resolution and can't predict small scale stuff. So we take that and then historical observations of heavy rain or tornadoes or whatever to use as the labels for training. And then, and so we're using random forests for this at this point is the algorithm we're using. And then we take today's output of the weather forecast model and run it through there to get the kind of hazard predictions. So it's not like 5 years ago, it probably was like a super sophisticated method. Now, like people are doing way more than that. I mean, it works pretty well, but there's certainly a lot more that could be done in that area. But yeah, I don't know if does that answer your question or yeah. And so the weather model, like the GEFS is going to be incorporating remote sensing observations, weather stations, weather balloons, all the, radar, all the things. Yeah. Yeah.
Maximum time when it was then I got the alert. sometimes what happens in the field, irrigation is already done. If they are concerned enough that, yeah, this storm is coming, then that water for irrigation can be conserved. So how is it?
Yeah. So yeah, follow-up question was kind of on, yeah, like how use of applications of weather forecasting in agriculture, essentially, and that doing your irrigation is very sensitive um to how much it rained, or being able to know what, how much rain there is. So yeah, so like what we've focused on mostly here is the like extreme events, the big ones, the ones that you're getting an alert on your phone for, that are often a bit more, well, I don't know. Yeah, they're high impact, but usually that's from the perspective of like flash flooding and things like that. For agriculture, a lot of times, I'm guessing, right? Like what you really need is you need those day-to-day thunderstorms that are coming through. Like, is that storm going to rain on your field so that you need to water it or not? And that's still really, really hard forecasting problem. Like the bigger the scale of the storms, the easier they are to predict in a general sense. It's those like little thunderstorms, in the afternoon that form and move over that are still really hard to predict. And yet we hear from farmers all the time too, that it's like, yeah, it's the set, forecast said it was going to rain an inch and it didn't rain, or the other way around. And it's still like, it's still a very active research thing. Some of it is just, we are limited by the fact that the atmosphere is chaotic and there's only so much you can do. But at the same time, there's still gains to be made in that area, because it's what, everybody wants to know is is it going to rain or not, and how much.
We take a question from Fort Lewis College. Do you have any?
Otherwise, there's one in the back here. If that, yeah.
Non-stationary extreme rainfall is the historical data they use to train them have like stationary extreme rainfall.
Yeah, great question. So yeah, question was about training machine learning to make weather forecasts or climate forecasts when you have to assume a stationary climate. Yeah, I think we don't actually know the answer to that question yet. So on the one hand, the weather, the dynamical physics-based weather models that we're using as the inputs to our system, for example, are like, if it's warmer, they know that it's warmer. And so from that sense, like that information is included. And so it's not that big of a concern. But on the other hand, essentially the way we've trained our model is based on a stationary climate on like frequency, like we're using ARI, like average occurrence intervals is essentially how we define an event. And so that will change in the future. And right now, I don't think we know what to do about that. So it's a very important question. And then now, right, like entire weather prediction models, entire climate models are being built around AI. And that becomes a really big issue there, because then the only data that it has is the data it was trained on that doesn't include the warmer climate. So in a couple of weeks, that we're actually going to be discussing this exact issue in our class. So if you want to come pop out and sit in, because this is, yeah, because there's a couple of recent papers where they try to kind of look at this issue, at least from like the climate modeling space. But yeah, this is a great question and a very important issue that I'm not sure we know the answer to yet. Yeah. Yeah, also a great question. So that's going to be the other part of that same class session. So the question is about, yeah, like using trying to do attribution of extreme weather to climate change. So yeah, this field has actually really evolved a lot in the last 5 years or so, because there's there's these large ensembles of climate model runs now. So essentially, it's easier to come up with like a counterfactual of this is what the statistics would look like without climate change and what they look like with climate change. And so, it's not perfect. It's not a perfect method, but it's a more robust method to then be able to say, well, this event fell even outside of outside of the envelope of what could have happened in the current climate, and thus we can attribute whatever, that there's a climate change fingerprint on that. And so for some things, it's becoming like extreme rainfall. Those fingerprints are really clear now, especially in like hurricanes. There's so much evidence showing that the oceans are warmer. The air, when it's warmer, there's more water vapor in the air, and then when you get a big storm like a hurricane, it rains more. Or heat waves, similarly, like that attribution's somewhat straightforward. But then other things like, wildfire is an example, right, where it's really tricky. Like there's climate change like influence on the weather that happened, or the drought leading up to the fire, but how do you incorporate the health of the forests or whatever, managing, or suppression of fires in the past? Like that's the kind of stuff that gets real tricky. So you can do some attribution on aspects of it, but then, all that sort of problem, or even floods for that matter, like the rainfall piece maybe is sort of straightforward, but then how do you translate the fact that it rained 20% more or whatever it is to like, what did that do to the flooding? Because probably that area was built up, the landscape was changed, the land use was changed over time, and that's where it gets a little trickier. Or Colorado River flows on the long time scales, right? Like we know the supplies have gone down because of climate change, but also demand has gone up, and so you can sort of attribute the supply side to some extent to climate change, but like, how does that relate to irrigation use, or who has the water rights, and all those things is trickier. Yep, exactly. Yep, and also like we know the like that, and that's the what I wrote back to the person asking about the 30-year versus 15-year records or whatever, was like, what I would, is probably harder technically, but use the shorter time period for temperature and use a way longer time period for like way longer than 30 years for precipitation. Because it's like, sometimes you go back looking in the old records on rainstorms and floods, and it's like mind-boggling how big some of these storms were, but they're really, really rare, right? So if you're only looking at, if you care about a 1,000-year rainstorm and you only have 30 years of data, like you're probably not doing very well with estimating that, right? So yeah, I was involved in this study that came out recently. It's relevant to engineering on this concept of probable maximum precipitation. Basically, it's used for constructing infrastructure like dams and nuclear power plants. It's meant to be like an estimate of, this is the most rain that is possible in this watershed or this location over some time duration. And a lot of those numbers are, so essentially what the number is controlled by one storm that happened in the 30s or the 50s or last year or whatever it might be. And then kind of assuming that you can take that story, you can take Hurricane Harvey and move it around all over the Gulf, and that's your number, or like, the 2013 storm, well, that's not even close to PMP for here. So that, it's like ideally you have thousands of years of data to be able to figure this stuff out, but unfortunately we don't have that. And so that's where you get to use your statistical knowledge or machine learning or whatever, creative techniques that can come up with. Okay, thanks.